Good morning.
Good morning.
Oh,
Good morning.
I can see my beautiful Winslow students today. How lucky am I? So, anyway, thank you, Miss Lopez, for getting that fixed.
Go ahead.
You're welcome.
So, let's go ahead and call the roll here. Rex.
Here.
Alana.
Here.
Tiana.
Not here.
Thank you. Taylor.
Here.
Aubrey.
Here.
Cameron.
Here.
Andrew.
Here.
Shandon.
Here.
Junior.
Here.
Caden.
Here.
Jordan.
Here.
Ellie.
Here.
Dominic.
Here.
Brooke.
Here.
All right, so we only have Tiana absent. All right, so today we have just a little bit to do to finish 8.2, and then we'll work on the last new material that's on the midterm will be on 8.3. So even if we go to 8.4 on Thursday or Monday and Tuesday after spring break, the material on the midterm is only going to be on up to 8.3. Okay? All right, any questions, comments, concerns before we jump in today?
I was wondering if we were gonna have like a review day.
So what we could do if you want to have some questions for the substitute. The bad thing is that 2 days before the midterm, I'm not going to be here. I'm not going to be with you. So the good thing is that you could get another perspective on how to do some problems. The bad thing is you might get a different perspective on how to do the problems. So I don't know. So do you want me to have, I can have the substitute say, okay, be ready or ask for question, do a question and answer session on those days to review. Would you like that with the substitute, or do you want to do a little Q&A on, we could do it the day after tomorrow, but then that's like before spring break. So how would you like to see that happen?
I think it would be helpful if he helped us.
If who did?
Like the sub answer.
The sub? Okay, so then what I will do is on my lesson plans for both Monday and Tuesday, when we come back from spring break, I'll ask him to, it's actually going to be Mr. Fritz. The guy that does the tutoring on Wednesday, he's going to be the one covering. So, he knows exactly what's going on. He's teaching out of the book and so on. But he, probably has a different way of doing things or whatever. But I think that could be very helpful. So what I'll do is in my lesson plans for those days, I'll just allow for a certain amount of Q&A at the beginning. And so you can ask him anything from chapter 6 through 8.3 to review for the midterm. Okay? Fair enough?
Yes, thank you, Mr. Strong.
You bet. Now, as far as what you could do, I would recommend looking through those in the book. Here, let's go to. Okay. So in the book, there's at the end of each chapter, there's like a chapter test and a chapter review. So I would, the chapter tests are shorter. So, I mean, I would recommend that you do like the chapter 6 test and the chapter 7 test just to kind of get yourself refreshed on those and check your answers in the back. And then if there's some that you don't get, then ask Mr. Fritz those. Those would be a good, kind of a good place for review. All right. Any questions on that?
Yeah, I was just wondering, is the format for the midterm going to be the same as last semester?
Yes. Yes. So you'll have part 1 on Wednesday, part 2 on Thursday, and then your overall score will be the average of those two. All right. And they are open book, open note. And anyway, okay. Anything else? Okay, the only thing I am a little bit nervous about is like I remember either the midterm or the final. I'm thinking it was the final. There was like some kind of a technical glitch in Winslow and we had to scramble a little bit. Do you remember that? Anyway, so the problem is I'm not going to be available those days because I'm going to be interviewing that VP candidate. So if something like that were to happen, just know that we'll make it up. We'll make it good. Okay. Well, if I have to open it up and if your computer dies or something, we'll figure it out. Okay. So don't panic, but you probably won't be able to reach me that day. Okay. All right. Any other questions or concerns?
Will you put a curve on this test just like you did on the last midterm?
Yep. I do curves on the midterm and the final. Okay. But it's based on all my trig classes. So, and I teach 3 of them this semester. So, okay. You don't need a curve anyway, Ellie. Come on. All right. All right. Well, let's go ahead and get started here. I just forgot to share. It's always nice to share, kids. All right. So we had this little bit left in 8.2. So it says, to graph polar equations using a graphing calculator, set it to polar mode. Now, in 8.3, we're actually going to learn another mode. So you kind of have to keep this straight. All right, so let's say I wanted to graph r equals 2 sine theta. So I just make sure I'm in polar mode, and then I just type it in, the r equals, and you end up with something like this. Now, what we want to do is to be able to classify it by its symmetry and its name. Okay? Does anybody remember what this is called when it looks like a flower?
Roses.
It's the rose. And it's symmetric through this vertical line. Now, in the XY plane, in the rectangular system, we call that the y-axis. Does anybody remember what that line is called in polar form?
Line theta or pi halves.
Theta equals pi halves. So, because pi halves, that's the angle. So that's the line where the angle is pi halves. So that would be the symmetry. Okay? So you would say it's a rose, and the symmetry is theta equals pi halves. All right? So now I want you to graph practice 5 in your calculator and then just do a rough sketch of it and then say what is what is it called and what's its symmetry. Okay, so Shannon, I know you weren't here yesterday. Did someone show you how to do it in polar, put it in polar mode? Put the calculator in polar mode?
Not yet.
Okay, so
Or
press mode, and then go down where it says function, and then you'll arrow over until you see polar. Okay? All right, now, when you press the y equals, it'll come up r equals. And so then you just type in 1 plus 2 cosine theta. And the theta you get from the variable key that normally gives us an x. In polar mode, it gives us a theta. So type in 1 plus 2 cosine theta. Okay? So now, were you able to get, were you able to get this graph okay?
Yeah, that's what I got.
Okay, great. Okay, now, can anyone tell me what type of one that is? What type of polar graph that is?
Lima.
Yeah, it looks like a lima bean, okay, and it's called a limacon. All right? And what about the symmetry?
The polar axis.
The polar axis, because it's a long here. So the symmetry is the polar axis, and it's a limacon. All right, excellent. Okay, so any questions on that? Okay, so let's. Were there any questions on 8.2 before we leave it? All right. Well, let's go ahead and go to 8.3 then. I'm barely staying ahead on these guided notes. This VP search is killing me. It's taking up all my time. But anyway, at least I was able to send out the guided notes on this yesterday. So, Joseph City, did you guys get it? The guided notes?
Yes, we did.
Awesome. Okay. So parametric equations is what this is called. So we're going to talk about how to sketch parametric equations and what a parameter is and how to get rid of it, how to get one, how to construct parametric equations. Okay, so this is when we have an equation that's solved for y in terms of x, or an equation in x and y, that's a Cartesian or a rectangular equation. That's an equation that's on the xy plane. All right? Now, the thing is that sometimes we want to involve a third variable. So actually what we've done so far in trig this whole time has been using parametric equations. We didn't call them that though, but it's when we have two equations, two variables in terms of a third, okay? So like if I have x equals cosine theta, y equals sine theta, x and y are in terms of a third variable. And that third variable is called a parameter. And these then are called parametric equations. Now, what it does is it allows you to focus on just one part of it. So like if we want to focus on, okay, these are the values for sine and cosine separately, then that can be very helpful. That's how we create the unit circle, is actually through these parametric equations. Now, okay, so let me ask a question. All right, so raise your hand if you're on your school's baseball or softball team. All right, so I have a question for you. Anybody can chime in though. You don't have to be on the team, but if the best home run hitter, is it necessarily the person who hits the ball the hardest?
Yes.
You think yes? Okay. Well, I would beg to differ because I knew a guy that I played with, and he hit the ball really hard, but he never hit home runs because they were always just line drives. I mean, yeah, sometimes he'd take out the third baseman, and he would hit the ball hard, but they were always line drives. He never hit home runs. So then my follow-up question is the best home run hitter the person that hits the ball the highest?
No.
No, because I'm sure you've all played with someone that it seems like every time they go to bat, they hit pop flies. Just goes straight up. And yeah, it might go up really high, but that's not going to be a home run either. So what you actually want to be a home run hitter is to have a combination between the height and power. You want to be able to see like here, this is the graph of, let's say, the flight of a baseball, and here the origin is like home plate. Okay. Now what we can do is actually break that down so that we can analyze the flight of the baseball in terms of its distance from home plate or in terms of its height. And so then we can analyze where we need to improve our swing. Have any of you ever seen the movie Moneyball? Moneyball is all about how a team in Major League Baseball was the Oakland Athletics, but then it actually became the Boston Red Sox, where they use math to succeed in baseball, and they use what they call analytics. There's no sport that I know of that uses math more than baseball, and especially at the major league levels. I mean, those guys, they can tell you that this runner has a certain batting average with 2 men on, and there's with 2 outs. You know, they'll have all the scenarios, and they'll know in which situation which utility player is better to put in. And they analyze things for the salary cap. They'll look at so many statistics. But one of the things is like the home run. How to achieve the best home run. What's the best angle on your swing? Okay? I guarantee you that if you make it to the major leagues, that's one of the things they do is they will analyze everything about what you do and try to maximize it. Okay? And it's all about math. It really is. So what we do is, okay, so if we have functions, all right, then it's like we can break down the functions into an x component and a y component. And so those are the parametric equations, and t is the parameter. And so it's like we focus on, say, the horizontal and the vertical components. Now, this is not only just done in baseball, but it's done a lot in like physics. In physics, you know, if you're trying to analyze what's happening in a physical situation, there's all kinds of forces that act on things, and so it can get really complicated. So what they do is they'll take every force and they'll break it down into its parametric equations. And they'll say, okay, these are all the vertical forces, these are all the horizontal forces, and then they can add them up that way. Okay? All right. Now, we're going to start off with the idea of plotting parametric equations. So by plotting points in order of increasing values of t, you can trace a graph in a specific direction. This is called the orientation of a curve. So this is kind of the first big difference in a regular graph. Okay? So like if I were drawing a regular graph, it might look like this. But when you're graphing parametric equations, you'll see those little arrows to show actually which way it's going. All right. So again, if you watch like the Weather Channel and you're trying to say, okay, which way is this cold front moving in? They'll actually have something like this with the arrows to show which way it's going, so that you don't, I mean, otherwise you could interpret it either way that it's going. And so the little arrows are helpful. Okay, so the way that we do it, so we'll have, again, parametric equations. You have these two equations in terms of t. So to graph it, what you do is you just pick any value for t. Now this is telling you that t is between -2 and 3. So what we can do is say, all right, let's start with t is -1 and go to 3 or whatever. All right, so then what we do is we start off with -2 and we plug that in for x and y. So -2 squared is 4, minus 4 is 0. -2 divided by 2 is -1. So we graph the point 0, -1 on the xy plane. The difference is that we also say what t is on the graph. So we actually have x, y, and t value on the graph. Then you go to the next value of t. All right, if t is -1, you plug in -1. So 1 minus 4 is -3. -1 divided by 2 is -1/2. So the point -3, -1/2. And so you put a little arrow here on the graph to indicate which way it's going. Okay? Now, the arrow is important, like I said, in physics and in analytics, in statistics. You have to know which way you're going. All right? Now, one of the things I do not like about how your book teaches this is that they don't put in the arrows. This is the first book I've ever seen, and I don't like that. Okay? Now, so I'm just wanting to warn you that I don't like how the book is teaching how to graph this. Okay? Now, so if you go to practice 1A on your sheet, it says make a table. So let's just make the table first. All right? So for t, in the first column, let's just do -2, -1, 0, 1. Let's see, I think that's what we used here. Sorry. Okay. So for our let's see. Oh, I think we're missing one. So let's just go to 1. So -2, -1, 0, 1. So put that into for the t, in the t column. All right? Now plug in those values for x. Well, it says x equals t. So those are going to be the same. All right? Now y is equal to -2 times t. So for each of these values for t, multiply by -2 and write that into the y column. All right, so you should get these numbers right here, 4, 2, 0, -2. Okay, so we won't use this last column here. All right, so everybody good with that, with the table? Any questions? All right, so next what I want you to do is to plot those points. So the xy, just plot the xy points. So -2, 4, -1, 2, 0, 0, and 1, -2. So go ahead and plot those points. Okay, so now, whoops. Okay. So now what we're going to do is put in the little arrows. So when you plotted those points, you should have gotten these 4 points. So what we're going to do is the first one that you plotted, that's at t equals -2. So label that by the first point. Then you draw an arrow to the next point and then connect the dots and then label the next point at t equals -1 and then draw the arrow to the next point, label that one at t equals 0, then draw the arrow, and then your last point for your graph will be t equals 1.
So when we're graphing this, like when we would do other graphs, like the line would just extend all the way down. Will this extend or does it just stop?
It stops because it tells you specifically that t just goes from -2 to 2. So it stops on both ends. Okay? So usually what that means, like in like a physics situation, like say with the baseball, the ball will only be in flight for like 3 seconds. So like t will go from 0 to 3, and that's it. Okay? All right, so any questions on that? All right, that's a great question. Thank you. Okay, so now I'm going to show you how to do it in the calculator. So to begin by setting the calculator to parametric mode. All right, so we've been working so far this year in function mode. Yesterday we did polar mode. Now I'm going to show you parametric mode. So when choosing a viewing window, you must set minimum and maximum values for x, y, and t. So that's important. So like if t only goes from -2 to 2, you have to set that. Okay, and I'll show you how to do that in just a second. All right. So let's say I want to graph. This is the one that you just did for a practice. Okay, but now I'm going to show you how to put it in the calculator. All right. So let's. Okay, so we're going to go to parametric mode. So if we press mode, and so right now it's in polar. So right next to polar is parametric. So you arrow to parametric and press enter. Okay, now when you do your table setup, so it's window, I'm sorry. Press window. See, and it asks for T-min and T-max. So in this problem, it would said that T just goes from -2 to 2. So that's going to be important. So -2 to 2. And then the T step, usually that is like how often, how much T is going to go up each time. Usually that's 1. Now the X min and X max, that's kind of tough if you don't know, but if you've already done the table, see we already did the table and we had, let's see, so the X went from -2 to 2. Now, so if you don't know, you could just keep it as from -10 to 10 or something like that. But let's just do -10 to 10. Let's say we don't have the table yet. And same thing with the y's. Let's say we really don't know where those values go. So let's have the y's go from -10 to 10. All right, then when we graph it, Oh, I didn't put in the function. Sorry. Okay. I'm like, wait, that's not the right graph. Okay, so it's x equals t. So now in parametric mode, the variable key is t. So it's x, t, theta. Okay, so x equals t and y equals negative 2t. Okay, and so now when I press graph, wait, did it not do the negative? Yeah, it didn't do the negative. So negative 2t. Okay, so there we go. Now notice the calculator doesn't show the arrows on the parametric graph. And maybe that's why the book doesn't do them. But in every application that I've seen, they always include the arrows. And so you need to know what direction. So that's kind of why I show you how to do it by hand, is because you're going to have to add in the arrows. So you got to know where you're starting and so on. Okay? All right. So go ahead and try practice 1B. Okay, so when you get the graph, draw it for me in the air. Okay, so kind of like a sideways parabola. Yep, so that's it. All right, and so it's actually going to be going this way. Okay. Why is this messed up here? Yeah, my T's are kind of messed up, but it goes this way. All right. Now, it wants you to know, using the vertical line test, determine if y is a function of x. So is y a function of x? No, it's not. It would fail the vertical line test. See, in function mode, we can only graph functions. So this is a way to graph those sideways parabolas that aren't functions. See, we never learned how to do those on the calculator. One way to do it is to put it in a parametric mode, and then you can graph all kinds of stuff. Okay, it doesn't have to be functions. All right? Okay. All right, now, there's two functions that when we break down like motion from the vertical and the vertical and the horizontal, these are the two equations you need to write down. Okay, so the vertical motion is y equals negative 1/2 gt squared plus v sub 0 sine theta t plus h sub 0. And so then I've got, so G stands for gravity, T is the time, V sub 0 is the initial velocity, H sub 0 is the initial height. The horizontal is much easier because you don't have to deal with gravity or the initial height. And so it's like these terms go away, the first and last, and so you just have V sub 0 cosine theta t. Okay, so what we're going to do is we're going to look at a setup here. Wait, one other thing. In this next example, it's important that you understand the idea of unit analysis, okay? Or it's called stoichiometry in a science class. But it's where, like here, we're starting with miles per hour. What?
Could you go back for like
Sure.
a couple? I got it.
Okay.
Thank you.
You bet. So like if we're going from miles per hour and we want to convert to feet per second, okay? So what you do is to convert like that, what you do is you multiply by a form of 1. This is called a conversion factor. So if we want to go from miles to feet, then you multiply by 5,280 feet in 1 mile. And so then the miles will cancel. All right, then you want to go from hours to seconds. So you multiply 1 hour is 3,600 seconds. And so then the hours cancel. So you put it either on top or bottom depending on what's going to make your units cancel. And so then to actually compute it, you're left with feet per second, and then the numbers, you start off with 100 miles per hour times 5,280 divided by 3,600, and that's how you get feet per second. Okay, is this new for anybody? Okay, I didn't think so, but it doesn't hurt to just do a quick little review. Okay, so what we're gonna says, suppose a baseball is hit 3 feet above the ground. So here the baseball's coming 3 feet above the ground, and that it leaves the bat at a speed of 100 miles per hour at an angle of 20 degrees from the horizontal. So here's the angle up 20 degrees and then 100 miles per hour. All right, so what we want to do is construct this set of parametric equations based on this situation. Okay? So, just looking at this, what is the 100 miles an hour? What variable represents that?
The initial velocity.
The initial velocity, except that everything else is in feet. Okay? And so then instead of actually plugging in 100 miles per hour, that's where we're going to put it in as 146.7 feet per second is the initial velocity. But we get that from the 100 miles per hour. All right, then what's the 20 degrees?
The sine theta.
That's the theta. And so you'll put that in for both parts. We'll take the sine of 20 and the cosine of 20. Okay? And then what's the 3?
The initial height.
That's the initial height. All right? So when we put those in, let's see. So when we put those in, the y, so that's the height at any time, would be -1/2. Now, where did this 32 come from?
Gravity.
That's gravity. So gravity in feet per second squared is 32. If you're working in the metric system, it's 9.8.
Should it be like a -32?
Well, the negative is with the 1/2.
Okay.
But yeah, it's built into the equation. You're right. Okay? Because, yeah, it's pulling down, so it would be negative. So, but they just built it into the equation right there. So, -1/2, 32 t squared plus 146.7 sine of 20 degrees times t plus 3. So, that's the equation that will give us the height of the baseball at any time t. Okay? So we can plug in after 1 second, it'll tell us, we plug in 1 for t, it'll tell us how high the baseball is. Okay? Now the x equation is a little simpler, but it tells us how far out the baseball will be, how far from the plate, horizontally. So that's 146.7, the initial velocity in feet per second, times the cosine of the angle, times t. All right. So, what I want to know, and you guys help me see if we can figure out how to find this, okay? How to figure this out. So, based on that math information, okay, what we want to know is this going to be a home run? All right. Now, a couple things we need to know is that it's hit right towards center field, and this is a major league park, and the fence is 400 feet from home plate, and the wall is 10 feet tall. Okay, so what we want to know is this going to be a home run? Does anybody have an idea of how we could figure that out?
Do we have to use that horizontal formula now?
Okay, well, so what would we do with it?
Well, the horizontal, after you solve for t, you can find out what x is, which will give you the length. And then after you solve for, so you could graph it. Could you graph it to get the t?
Oh, okay, so you could graph it. You could put this in your calculator for your y and your x, and you could do it that way. That is actually one way that you could do it, is with the graph. Okay? So, but what else were you talking about? How would you solve for t? What is it that what did you mean by that?
Well, like, I don't know. Like, when I do this in my other class, we just have like a list of other things we solve for in different equations.
Okay.
But those,
So, I mean, but there's, which one are you going to solve for t? The x or what?
the x, right?
Okay. So then what are we going to plug in for x?
Then use the answer to what that whole thing.
Well, actually, what we want to know is when the ball is 400 feet away, is it going to clear the 10 feet high fence? So if we actually plug in 400 here, then t will tell us how long it takes to get 400 feet out. Then we can plug that up here and figure out how high it is. Does that make sense?
Yeah.
Okay. So I want you. Well, I guess let's just try to work this through together here. So we're gonna, let's see. Okay. So if we plug in 400 for x, and then we got to work this out. So 146.7 cosine t. If we divide that by 400 divided by that, we get t equals 2.901 seconds. Okay? So that's doing exactly what you said, Ellie. So what does that mean? What is 2.901 seconds? What is that?
It means that in 400, it'll take 2.9 seconds to go 400 feet.
To go 400 feet from the plate. Okay, so again, that's a horizontal distance. So now, how do we figure out how high it is?
Well, it's the same time, so you just plug the t in the top equation.
Into the top one. All right, so I'll let you do that one. So plug this in for t here and here into this equation and see if you can figure out how high the ball is. So we're plugging in 2.901 for t here and here, and then you'll just put all that in, and then you'll get the y value. Just let the calculator do all the work. All right, so Shannon, when you've got it, tell us what the y value is. All right, hold up. Okay, I guess we're having a fire drill. Well, maybe not. Let's see. Are we clear? Did you guys put out the fire? Oh. All right, so Shannon, did you get it?
I got 13.9.
Okay, so is it a home run?
No, it's not.
Okay, if the fence is 10 feet high and if the ball is 13 feet high, it's going to clear the fence.
There it is.
So it is. Does that make sense? So we wanted to know if the height is going to be higher than 10 or not. And so since it's higher than 10, now, if you have a really athletic center fielder, I don't know if any of you have ever heard of Bo Jackson. He would like climb up the side of the wall, and he could probably catch it 13 feet high. But most of the time, that's going to clear. That's going to be a home run. Okay? So any questions on that? All right. So the next thing that we want to look at is eliminating the parameter. So this is kind of where you have the parametric equations and you want to go back to rectangular form. So the process of converting from parametric form to rectangular form is called eliminating the parameter. Okay? So these are the steps. First, you have parametric equations. Then you solve for t in one equation. Then you substitute into the other equation. And then you end up with your rectangular equation in x and y. So just going through this again. You start with your two parametric equations. All right, so if you solve for t in this one, so multiply each side by t by 2, and you get t equals 2y. Then in place of t in the first equation, you plug in 2y, simplify, and then you have an equation without t in it. So that's called eliminating the parameter. All right, so see if you can do that in practice too. Okay, so which equation is easier to solve for t?
The y.
Yeah, it actually, they're both about the same. Here, let's see, I solved it for the x. So here, I multiplied each side by radical t, and then solve for a radical t, and then square both sides. But really, it's about the same either way. So you get t equals 1 over x squared. So that's solving for one of the either of the t's. Then you take and put that in place of t into the other equation. All right? So you have 1 over y equals 2t squared. So then in place of t, you have 1 over x squared, right? That's what we got. So now you're going to have 2 times 1 over x squared. So that's 2 over x to the 4th. So that is your equation. Y equals 2 over x to the 4th. That's your equation in the Cartesian. All right. Any questions on that? Hey.
Jeff?
Oh, yes.
So, we kind of messed up in Joe City, and I don't think any of us have done any of the Chapter 7 stuff because we like completely forgot that it was due yesterday. And so none of us have gotten any of it done. Is there any way that we can make it up?
Yeah, send me an email and tell me exactly what it is that that you need or if everybody needs. Okay. But you're going to have to get it all made up before the midterm.
Okay.
Okay. But I can do extensions or whatever.
Okay. Thank you.
But yeah, it has to be done. Okay. So the last thing, really quick. I don't know if we're going to have time here, but it actually is the easiest thing in the world. But we might have to wait and do it next time. I can't even find it now. Oh, actually, I did want to include this.